All right, hello, good afternoon, or morning, or evening. Um, Today, in this video, I'm doing a recap of what we covered in the last 2 days or so, and it's gonna take less time than in class because I'm not trying to get the feedback, the back and forth. We're just gonna cover what we have right now. So, a couple of announcements. If you want to turn in late work, please feel free to do so. Assignments 7 and 8 were graded this past weekend. If you want to update that, let me know you did. I can go ahead and update your grade. And that goes for all their assignments as well. Feel comfortable in saying that because very few take advantage of that. So today we're covering entropy, right? That's the notes that we did on Wednesday, December 2nd and December 1st. On Friday and Thursday, we'll start and hopefully finish assignment number 10. And on Friday, assignment 9 is due. So make sure that's completed in your notebooks. I'll be checking that over the weekend. Friday is also an odd professional development day, so do keep that in mind. And on Friday also, I will be releasing our final just in advance. You don't have to get started with that, but if you want to, you can. Now, I believe I am sharing the screen and everything is set. So let's just take a look at what we have. Now, you should have clicked on the notes on entropy and then just copy and paste that into your notebook. And I've kind of already done that here. And so this is what we're working with today. We know that everything is made of particles. We know that those particles are always moving around, right? Even if it's a solid like a quarter, right? A quarter is very solid, but the particles that make up that quarter are vibrating in place. They're moving around, right? Gases move, liquids move, those particles are always moving. And what we want to know today is how do those particles trend? Like, are they going to become ordered as time goes on, or are they going to trend toward being disordered? And that's where entropy comes in. So what is entropy? We filled in the vocab for that, so let's just go ahead and do that. The vocab for entropy in your book, in your textbook on page 96, you'll find the definition. It's just entropy is used as a term to describe how ordered or how disordered or how unorganized a system is. And so the go-to example I've been using has been, imagine 20 or so kindergartners, right? Imagine a classroom, just complete chaos, right? Books on the floor, glitter everywhere, glue on the tables, chairs flipped over, kids running around covered in mud, and worst of all, there are Legos on the floor that anyone could step on. So it's a very disordered system. And so that is an example of a high level of entropy. And so we use the letter S to describe entropy in mathematical equations. We're not really talking about the math in this video today. Most likely we won't be doing that at all, but it's pays to know. So S, I'm under the assumption that S stands for system and surroundings, as in that's what the entropy is affecting, but yeah, S is the symbol. And so the first part of our notes is to create some examples of high and low levels of entropy. High entropy typically means that system is very unorganized, it's very disordered, right? Everything looks very random, and we as humans typically assume that is very bad. Low entropy, on the other hand, is very organized, very ordered, right? And again, as humans, we think that's good. We like a little bit of order in our lives. Now, I say good and bad, but that's not necessarily a thing. That's just people putting, feelings onto natural systems. But it's a good way to describe it. And so, if we're keeping that in mind, think of this like golf, right? The lower your number, the better your score, right? And so, when it comes to low entropy, we really want organized systems. So things like a high school or like a prison, where you have set times to do set things. You have to dress a certain way. It's a very ordered system versus a kindergarten class where all the kids are running around. It's very chaotic. Think about protests. Protests are very ordered, right? You go march in a certain direction, you have certain slogans to yell, and you have a purpose in mind versus a riot, which is a complete breakdown of order. A corporation, typically a very well-managed corporation, is very organized. CEOs at the top, mid-level managers, and employees, versus a small business, which is just like, you know, three people who know each other well. Food, right? Food is very organized. Think of an avocado. You got your thick skin, your green flesh thing, and your giant seed in the middle. And then imagine blending that food. Blending that food is mixing that. You're disrupting that order that that food had. We have to go over number one. I'll reach that in a second then. My classroom. If you have stepped into it, it's very ordered. I have things in a very certain system, and I like it kept that way. A typical student's bedroom, on the other hand, probably not very ordered, probably, dare I say, even messy. And so you have organization versus unorganization. You have order versus disorder. And this applies to not just systems and society, it applies to particles, right? Let's say I have metals, right? A metal particle, right, is very ordered, very rigid, very structured. But if I were to apply heat, that metal will start to melt. And when it does, those particles become very disorganized. And so entropy is starting to increase. Steam and ice, right? Take a look at this image here that I skipped now. Ice is very ordered. The structure of those particles is very rigid, very safe, very, boom, boom, boom. It's very rigid. Water, on the other hand, is very free flowing. And so ice melts, and we could fix that by just removing the heat. But for the others, wood burning, dyed sugar dissolving, it can't really do it. You can, but the energy required to reverse these processes is not worth it. And so that kind of relates to chemistry, and I'll get to that in a second here. Let me just finish this discussion off. Our solar system is a very ordered system. We have the sun, we have the planets, we have the asteroid belt, more planets, more asteroids. It's a very ordered sphere. Now, as time goes on, that system will become disrupted. It will become disordered. And so entropy will increase. The size of our sun, right? It will go from the yellow star it is right now to a red giant. And when it does, it's going to eat up Mercury and Venus and possibly even the Earth. I don't really know the exact dimensions, but it's going to get big. And when that happens, we could say that the entropy has increased, right? The sun has become disrupted, it's disordered. Those particles have taken up more and more space. So entropy has increased. There's less energy to go around now. And in trillions and trillions of years, that process will continue and it will end the universe. And this is kind of why this topic is my favorite. There are so many different ways entropy will kick in, and the leading theory is this thing called heat death. Now, it's not the idea that everything is going to get hot. It's more the idea that nothing is going to get hot anymore. Heat is done. Heat has died. And so there's other names, the big freeze or the big chill. And it's the idea that there is no more energy left because entropy has maxed out. There is no more places to sustain entropy. There's no free energy to go around. And so things just kind of chill out, right? No more hot yellow stars. All we get are white stars that will transition to being black dwarfs. And so that's how the universe ends, not with a bang, but with a ever increasing slow march of entropy. Now, don't let that, worry you. Don't let that existential dread kick in. It's trillions and trillions of years away from us, so don't even worry about it. Now, other image, that first image here. For the wood burning and the dyed sugar dissolving, entropy has increased to the point in those systems where it's just not worth it to undo, right? If you had to undo it, you can, but the entropy involved is just not favorable. And so this is a thing that applies to any kind of chemical reaction. Chemical reactions could only be really undone by other chemical reactions, and that requires energy. Now, let's take a look at this question here. A fridge has cooled down water particles and turned it into ice. Describe what happens to the entropy in that system and where the heat goes, right? And so let's break that down. Water is very loose and free-flowing, so it's very disordered, and so the entropy is very high. Ice, very rigid, very structured, and so it's very ordered, so the entropy is very low. And so it looks like you beat entropy somehow. You turned high into low, and you cracked the code. But think about this. To turn water into ice, you had to remove the heat, right? So you had to remove some energy, right? Form those bonds up again. And to do that, right, you put your water in the fridge. But the freezer, is powered by something. So guess what? That heat that was inside that water, keeping it liquid, has now been put outside into the atmosphere. And so overall, your entropy has increased. So even though you lower the entropy in one thing, overall, the entropy has, increased. And so there's no stopping it. This is the second law of thermodynamics, right? The idea that entropy will always increase no matter what you do, right? Taking a breath increases entropy, right? You've added heat out into the space around you. You've disrupted the gas. And so to go back to the driving question here, all particles trend towards disorder. Everything will eventually fall apart. And so when that happens, we've reached max entropy and the universe ends. But until then, let's look at these phases here. We have gases, solids, and liquids. And in class, I just asked you guys, what is it? Is it low, high, or medium? And so we have that set up here. Solids, very low in entropy, right? Very organized, very low in entropy. Gases move around very fast, very willy-nilly, no real rhyme or reason or pattern. So it's very high in entropy, very disordered. The liquids are very much our middle ground there. So they're medium entropy. Now, as far as chemistry is concerned, entropy is neither good nor bad, right? We need a little bit of entropy in order to do some reactions, right? To have two solids react to each other, it's kind of hard. You need a lot of energy to break those bonds and get the solids to react with each other. If I have two quarters in my hand, I'm trying to react them, nothing is really happening here. And so we use liquids and gases because it's easier for those particles to, collide and actually perform reactions. And so we need a little bit of entropy, not a lot, but like we need it to get reactions started. So entropy is how disordered a system is, and it exists all around the world. Earthquakes, right? It's not exactly a change of state involved in terms of earthquakes, but the energy for them comes from the earth, right? The earth is moving around, so those plates move, and when they collide or move around, we got some earthquakes. Energy is not being created or destroyed, it's just being transferred from the inner, or actually outer core really. It's being transferred from one place to another, and that is releasing energy, all throughout the world. It's releasing energy, and when energy is released, those particles become more and more energized and more disordered. And so entropy is increasing, right? So let's take, winter, right? Ice is formed. Well, the energy left the water and entered the atmosphere. And so energy is not being created or destroyed. The energy that's in the atmosphere now, is just going to continue spreading. So the energy is going to enter the atmosphere. You already say this, and increase the disorder in those particles. Again, increasing entropy. So even though ice is formed, and ice is very low in entropy, even though ice is formed, entropy is overall always increasing, no matter what. And so it's one of those things you can't escape. It's like a horror movie monster. You just can't escape it. And that makes it a really fun topic to go with. And that's pretty much it. This took a lot longer in class because I spent more time just creating that discussion, engagement. So this is a recap video. So hope you enjoyed it. On Friday, I'll have another video for assignment 10, hopefully posted, and I'll see you then. Until then, bye-bye.